Good morning. I'm going to continue with my discussion on information, entropy, and black holes. Now, information is a large topic. Information, think Shannon, Claude Shannon, 1949. And he has an entropy formula which is similar, very similar to the entropy formula of Boltzmann in thermodynamics. Now, we've been doing lots of different examples. We're going to continue with this now with a kind of open-ended discussion leading up to some speculation on the entropy of a black hole, okay? And why it should be the formula that it is. And, you know, I actually have to look up how Bekenstein derived it. Hawking takes some credit for deriving it more rigorously. I'm not exactly sure. I don't know that derivation either. That's subject for a class down the road, okay? So, first of all, let's talk about what we mean by black holes. Black holes were first recognized to exist by John Michell, who lived 1774 to 1827, but he did his work on black holes in, I think, gosh, I'm not sure. So I can't remember. John Michell did the work first. Laplace did his work in 1796, I kind of know that. And then this century, a great deal of applications were worked out by Subramanian Chandrasekhar. Chandrasekhar means bright moon. Chandrasekhar had 2 Nobel Prize winners. He got a Nobel Prize himself with Fowler for some of his work, and regretted that he didn't get for more of his work. They got the Nobel Prize, and Chandrasekhar had 2 students, Li and Yang, and they got a Nobel Prize too, right? Now, other reasons were earlier this century, J. Robert Oppenheimer, whose years of existence I can't quite remember, and Oppenheimer was, of course, as you know, the overseer of the Manhattan Project that built the atomic bomb, okay? But some of his earlier work is in black holes. Now, other people who did work on black holes would be Misner, Thorne, and Wheeler, who wrote this book, and the term black hole was coined by John Wheeler, who invented a few weird different terms as well, other ones. I prefer the original term by John Michell, dark stars. Now, dark stars come from taking the ordinary Newtonian escape velocity, formula that I actually derived in one of my gravitational lectures, and equating the kinetic energy to the potential energy, so we can derive, if we assume that the inertial masses cancel, the escape velocity of the surface of the Earth at mass m and the radius r would be given by 2gm over r. Suppose that escape velocity is the speed of light. Then the escape velocity is going to be (9 by 10 to the power of 16 meters the escape velocity squared. So the escape velocity is the square root of that. Okay, so that defines the Schwarzschild radius. Now, in general relativity, there is an expression. For what's known as the metric, the Schwarzschild metric, was found by Schwarzschild, Karl Schwarzschild, during the First World War. Now, in that result, only is there a constant, lambda. This result is put in by hand, which is kind of a foible, a flaw in general relativity, because the Newtonian result is put in by hand on purpose. That c squared, the escape velocity, is going to be 2gm over r, defining the Schwarzschild radius. So that defines a region inside of which you go, light can't get out, basically. Then there's a whole lot of other geometrical artifacts that take place. And whether or not the universe is a black hole or not, it's worth considering. Sean Carroll thinks it's a white hole. I'm not so sure. I'm going to look at that for another class. So that's what we're talking about with black holes. Now, the next thing, the entropy of a black hole is given by the Hawking-Bekenstein formula. Okay, Boltzmann's constant is K. Boltzmann's constant is the same as in ordinary thermodynamics, and A is the surface area of the black hole. And RS in here, that gives the surface area, is the Schwarzschild radius to be squared. Now this here is the Planck length. But squared. When we square the Planck length, we get a small unit of area. Which I'm going to call L0, okay? So that the W, which I worked in my previous examples, is dimensionless. This is dimensions of 0 as well, because entropy has dimensions of joules per Kelvin. This guy has dimensions of joules per Kelvin. They cancel, we get a dimensionless quantity. This is the information part. This W. Now, let's have a look at this little formula here. Get your hands around this one first. So we're not going to keep writing the Planck length like this. I'm going to write it like LP or L0 even, right? And that's to be squared. So let's have a closer look at this little formula here. Now the 1 over 4 is there for a reason. I don't know why people don't notice this. There is a view of the world called the holographic view of the world. Read anything by Susskind on it. And it says that all the information of the world can be stored on a two-dimensional surface. We do not need the 3. Let's get rid of this. I've discussed this in a previous class. So if we take our black hole, all right, it has the same radius. All the bits of information can be stored on this two-dimensional surface because it's just pi r squared. Now we've got this, right? That's an area. And this is an area. So this is an area over an area. And of course we have the k here still because I didn't get rid of it. This is going to be an integer. Kind of like the Bohr quantization condition 2 pi r equals n times lambda. But we're counting bits. The black hole area, let's say for a sun, would be, you know, the sun's Schwarzschild radius is 3,000 meters. So that the number of bits contained in this is approximately 9 by 10 to the power of 6 or by 10 to the power of 7. This is about 10 to the power of 7. If we're measuring it in bits. That's a lot of information, okay? So if we just deal with the information part. So now we know that we're dealing with an area over LP squared is an integer. The information part. So let's look at the problems that we were looking at before. This is the formula that's accepted to be true. Now I have a lot more to say on information, but that's coming up, not just yet. So I just take S over K, the dimensionless part, is A over A0, where A0 is the Planck length squared. Now I use this notation. If you look at other people doing stuff, they will do different things. They will write down different things. They won't use the W, they'll keep the K in there, so on and so forth. I'm just dealing with it this way. So in our examples, we did things like this. One example looked like this. We took a grid 16 by 16. Well, wait a minute. We then looked at the we looked at the entropy of this grid. As being log to the base 2 of Z. What is Z? Well, it's the number of accessible states. If we call a state a place where we can put a particle, then there's 16 by 16 accessible slots to stick one boson, okay? Two bosons, you can stick two of them in one. In fact, for one particle, we don't care if it's an electron or a photon. We don't care because we're dealing with one. The Pauli exclusion principle says that no two fermions can occupy the same state at one time, but bosons can. You can have any number of them in the same state. But notice that this is a log, right? So in this case here, 16 by 16 is going to be log to the base 2 Now 16 is 2 to the power of 4. So that the n in this case, when we take the log of it, is actually 8. The entropy for this one here is going to be 8. 8 what? Well, I took the W, 8 units of information. If I was including the K, then it would be a much smaller number. Now notice this is an area. Well, it's an area, 16 by 16, divided by the total area of each of these little cubes, right? Yeah, those little squares, it's the same thing. In this case here, we're still dividing an area, kind of like the Schwarzschild black hole, but the difference between the Bekenstein formula is that there's no log in the Bekenstein formula. So that has me bothered. I don't know why that is there like that. So I want to take the Bekenstein formula and write it in a slightly different way. Have a look at this. Okay? Oh, we had other examples. We started off, let's do Shannon's information for this one as well. Okay? The Shannon entropy. Well, I'm going to clear the board and do a simpler example for Shannon. I'm sticking with log to the base 2. It doesn't have to be that. It could be log to the base e, or 10, or anything. So, let's do the simple situation of, let's say, 8 possible states. 1, 2, 3, 4, 5, 6, 7, 8. Eight states, right? So the probability of being in this particular state is 1/8. Now, negative sign makes me bring the 8 upstairs. So I have 8 factors of 1/8 log 8 to the base 2. Now, did I do that right? Now, I may have made a mistake here. It's not what I'm expecting. All right, I'll believe it for now. The entropy for this case is 3. Now, let's just do it the way I was doing it. Now that's the Shannon entropy, that's the formula, and it works. It has a log in it. Before I was just writing down log of the total number of accessible states. 1, 2, 3, 4, 5, 6, 7, 8. Which is the same thing, right? Doing it in your head versus applying the formula. Now, I will explain where this formula comes from in a separate class, not in this one. I just wanted to look at the Bekenstein formula for a minute. The information part of Bekenstein's formula is the area of a circle over A0. All right? And it's going to be an n, okay? It's an integer. Well, let's see if we could insert an n into this. What would it have been if I had the z number of accessible states? Well, log 2 to the base 2 equals 1. So I could put in a log 2 to the base 2 in here. So therefore I would get s over k equals n times log 2 to the base 2 in bits. Now that is equivalent to a world with just two acceptable states, but n particles, right? That is the same result. We did go back and see what happens when we have several particles in my previous lectures. Lectures 1 and 2. This is lecture 3. So that leads me to suggest an alternative equation for the entropy of a black hole. And it's the thermodynamic entropy. would look something like that, okay? Now it's going to give the same result. But of course, that's not the way we write it. Now there's a factor of 1 over 4. They write it like that, where there's A is the surface area of the sphere. It's gone as far as I'm concerned because I believe in the holographic viewpoint of the world. Now I'm going to do this whole thing for the universe at some point, but not just yet. I still have time to talk in this lecture, so I might talk a little bit about information. Well, to actually derive information is kind of tricky, but we can see where we get a formula for it. How is it going to work out? All right. Well, we're going to say that the information is going to be defined as follows. The information is a function of the probability of X happening. Don't ever spell rose. I give you a statement, the sun rose today. What is the information? Well, let's see. The sun is definitely going to happen. Well, the probability of this event happening is 1. It's 100% going to happen. So we'll say that I(1) is 0, right? Now, here's another one. I bought a ticket. There were 1 million tickets issued, and there were $1 million of a prize. I won the prize. What are the chances of that happening? Well, it's a very small number. Well, the information associated with this is big. I have a 1/1,000,000th of a chance of winning this. And I chose the base 10 here just because it was easy. And I showed you guys earlier on in a different talk how to convert from base 10 to base 2 and vice versa. But just to make the thing easy, how did this work out? Now I may be making a mistake here with the sign. I didn't expect to see that. Anyway, one way or another, the idea of the log as being a definer for information seems to work. Now I wonder if it's 1 over P of X or P of X. Now I have to look that up. Okay, I'll have to correct this in in the next lecture. I'm not quite, maybe I made a mistake. I didn't expect a negative sign here. I'll come back to that. I'll post this one and we'll correct it in the next one.